Well, I guess we can get started. Thank you all for coming today. We have the pleasure of having this week Rita Tojeiro with us. She studied in Edinburgh before moving to Portsmouth for a few years to the Institute of, let me see that I wrote it down, Institute of Cosmology and Gravitation. And then now she moved to St. Andrews, where she's now a reader at the School of Physics and Astronomy. And at least I got to know about her for her work on stellar population fitting and analysis of galaxies. But then she's been also work on large-scale structure, CMB. And I guess so she moved a bit into larger scales, and then she's coming back to galaxy scales. And I think that's what she's going to present today. So thank you, Rita, and the floor is yours.
Okay, everybody can hear me? It's okay, excellent. So thank you, first of all, thank you for having me. It's been really lovely to be here. So as Nacho said, I'm going to talk to you a little bit about the connection between large-scale structure and galaxy. These are two things that sort of merged as I thought about them independently, and then I started thinking about them together sort of about 3 or 4 years ago, with a break of about 2 years, because you know why. So what we're going to do today is we're going to start talking a little bit about halos, galaxies, then the galaxy-halo connection, then the cosmic web, and then we're going to bring it all together. So just a brief overview of the galaxy-halo connection. You don't get my entire slide. That's okay. That's okay. So galaxy-halo connection is exactly what it says on the tin. It's the connection between the dark matter-dominated large-scale structure, in particular, sort of the gravitationally bound self-contained halos, and the galaxies as they develop and form and grow within those halos. And we've got a number of ways of describing this connection. I don't have a pointer. I did. Okay, I'll just have to describe things to you. That's okay. We've lost the pointer. No. No, it's okay. Don't worry about it. I will try to describe things. Keep in mind that I can't tell my left from right, so you might get really confused. No, it's fine. We'll cope. Right. Okay. So galaxy-halo connection. How do you describe this connection between dark matter halos and the galaxies that grow within them? There's a variety of ways. So this sort of became a sort of an iconic picture that sort of describes the complexity of the several ways in which you can do that. So on the right-hand side, you've got the simpler models where you're really just saying, okay, I'm going to have some halos according to their mass. I'm going to put some galaxies in them, and then you're going to evolve that relationship in time. At the other end of the scale, you model everything together. You model the baryons and the dark matter together. You have to make some assumptions, and in here there are assumptions at all levels, but you make fewer assumptions, or you make different sorts of assumptions as you go towards the left-hand side. Why do we want to study the galaxy-halo connection? Why is this important? Well, right at the top there, I mean, essentially is really a fundamental, it's a fundamental building block for us to understand how galaxies grow. So if we want to understand galaxies, we need to understand their large-scale context and the sort of environment of the halo in which they grow. But also, in order to understand, when we're doing large-scale structure experiments and we're trying to infer cosmological parameters or the nature of the universe on different way using galaxies, what you're really doing, sometimes explicitly, sometimes implicitly, is taking your tracers, what you observe, the galaxies, and making inferences about the underlying density field. And so understanding this galaxy-halo connection has implications for that as well. So whether you're a cosmologist, whether you're a galaxy evolution person, or you're in the middle like me, there's sort of value in thinking about the galaxy-halo connection. So I'm going to just give a really brief introduction to halos and to galaxies. So halos, for the purposes of this talk, they're just dark matter overdensities that have decoupled from the Hubble expansion, and they're gravitationally bound. And we have here is just a picture from a numerical simulation. And I'm just using it to exemplify what I'm going to often call halo or fringe of fringe halo, is this large overdensity within which you'll find some substructure. I'll refer to those as subhalos. And if I'm talking about central galaxies, I'm talking about a galaxy that is in the central subhalo. If I'm talking about a satellite galaxy, I'm talking about a galaxy that is in a subhalo. And now, what is good about sort of thinking about large-scale structure in terms of halo growth and in terms of these sort of self-contained units called halos is that from a set of sort of initial conditions, you can analytically or computationally work out some really basic and fundamental statistics about these halos. So you can compute their abundance, and you can compute their clustering, for example, and how they change as a function of halo mass. And so that's nice. It's nice that you can do that sort of analytically from first principles. In detail, this is more complicated, but to first principles, we got a good handle on this. And so, these very, very simple descriptions have sort of often hinge on halo mass as the describing variable of a halo. Therefore, if you know the mass of a halo, you know a lot of the relevant properties of a halo, such as abundance and clustering and so forth. This picture started being sort of challenged quite a long time ago now. 2005, I think, is the first time that we started thinking about this. What you have in these two pictures is an n-body simulation. Each dot there is a halo. They're roughly the same mass in the different panels, but in one of the panels, the halo is assembled earlier, and in the other, they assembled later. And they assembled earlier on the one on the right. And so you can see here is that there's a property of the halos, which is their spatial distribution, that doesn't depend only on their mass. And you can take this in many directions. And over the last 15 years, people have taken this in so many directions. But I just want to describe these sort of in very simple, sort of basic terms. This idea that this is hard without a pointer. If you look at the top panel, the top 6 panels, in each of them on the x-axis, you've got a measure of halo mass. On the y-axis, you have a measurement of the clustering amplitude of the large-scale bias. And then in each line, in each panel, you've got 2 lines, a red and a blue line, and that tells you that's how, the halos in those, they've been separated in 2 samples according to some property. And that property is sort of written in the panel. But the point is, if you separate halos in some properties, they really do have different clustering amplitudes. And here's something similar, but looking at halo age. So on the top 6 panels, you have things like related to the shape of the halo and to the velocity of the particles in the halo. And in here, you've got things related to the age of the halo and also its angular momentum. And so this whole idea that there's something else to a halo became known as assembly bias. It borrows its name from the fact this was first spoken about in terms of halo age, but now it can be a number of things. I will highlight this panel here because we're going to come back to it later. That's velocity anisotropy. It tells you something about the types of orbits that, in this case, the dark matter particles of the halo are experiencing, whether they're sort of radially or tangentially dominated. And we'll come back to it because that's a really good discriminator of clustering at fixed halo mass. Okay, that's halos. What about galaxies? Well, galaxies are way more complicated, prettier too. And there's good things about that. So most of you will be familiar with this idea that we can separate the galaxies into sort of 2 populations, a blue star-forming population, a spiral-dominated, and an elliptical quenched population that more or less separate in mass, but not quite. And so in many ways, we want to be able, hundreds of thousands of years of communal time have been dedicated to trying to figure out why this is and how galaxies become this way. Now, galaxies have the absolute advantage that we can see them, right? Which is not something we can do with halos. And so, sorry, just behind. I think this is not so relevant for this audience because you all know this, but there's really what we're trying to do is trying to find different physical processes by which galaxies become in one of these two populations, how they go from one to the other, and so forth. Okay, now, as I said, galaxies have the absolute advantage that we can see them, and therefore we can measure these fundamental properties. So we might not be able to predict from first principles their abundance or their clustering or their assembly history, as we can do with halos, but we can measure it, okay? And this is what we see here. So in the top left panel, what you see there is a correlation function as a function of luminosity or absolute magnitude of galaxies. You can see galaxies of different absolute magnitudes cluster differently. Here we can see their abundance, so we can measure stellar mass functions. And here what you have is a measurement of their star formation history. We cannot measure an assembly history, but we can at least measure the star formation history that tells you when stars in a galaxy formed, if not necessarily where. So we cannot write it down. It's harder to compute, but we can observe it. So it's just a wee bit slow. Okay, so let's start talking about connecting these two things a little bit more directly. So I showed you that plot there that says that galaxies of different luminosities cluster differently. So typically the way to link this is via halo mass. So we say that, okay, halos of different halo mass cluster differently, and galaxies of different luminosity populate different halos. And therefore, you get a dependence on galaxy luminosity on halo mass. But here, everything is happening through halo mass, and halo mass is indeed king. Now, another way of thinking about the galaxy-halo connection is this relationship. So what this is showing is what's called the stellar to halo mass relationship. So on the x-axis, you've got halo mass. On the y-axis, you've got stellar to halo mass. And if halos of all masses, if they all made stars with the same efficiency, this would be a flat line, okay? The fact that you've got a structure in this relationship tells you that some halos are better than others, or halos of different masses are better than others at making stars. And baryonic effects sort of dominate this relationship. And so common wisdom now is that there's very different processes happening at high and low masses. The high masses, you've got things like AGN feedback, and the low masses, you've got things like supernova feedback and other processes. So I'm not going to talk to you too much about the shape of this relationship. I'm less interested in that. What I'm going to focus about today is the scatter in this relationship. So now just focus on one of these, just focus on the top left panel, where I'm showing halo mass against stellar mass. So this is the same relationship, just plotted a little bit differently. And then what you have in the different lines is the median relationship for halos that formed at different times. And so what you can see is that a fixed halo mass, central galaxies that are in halos that form earlier, so that stores the red, they have a higher stellar mass. Okay, so your central galaxy knows about when the halo formed. And what you see is 4 panels showing the same thing, just different simulations. And but I believe, well, actually, I think in all of them, the same way of parameterizing halo age, which isn't trivial, but I think here it's all like when the halo reached half its present day mass. Okay. So now I've sort of given you a really, really brief tour towards what we mean by sort of halos, galaxies, and this idea of galaxy-halo connection. And now we're going to talk about a little bit about the cosmic web. Right, here she is in its full beautiful glory. This is the cosmic web in baryon density, so predominantly gas density in illustrious TNG. This is the full box, 300 megaparsecs on the side. And glorious as she is, and even though she's the poster child of the nonlinear universe, defining what the cosmic web is actually really difficult. And there isn't really a single way of doing that. You can think of doing this topologically, so by how the density field looks like. And you can see by eye that you can have these filamentary structures, and you've got underdense regions called voids. So you can take that approach. You can look at the velocities as well of the particles, not just at the shape of the density field. You can also look at the tidal tensor of the density field. And you can look at a number of these things and you can put them together and you can say, okay, these are different environments. And they correspond typically to things that we call filaments. So these are the sort of string-like things, nodes where filaments intersect, voids, which are underdense three-dimensional regions, and sheets, which are the two-dimensional regions that surround them. And just to give you an idea, I'm not going to go into it because this would be a completely different seminar, and honestly, let's not go there. But this is just a quick summary of nine different ways of estimating these cosmic web environments from the same density fields, from the same distribution, in this case, of simulated dark matter halos. And you know, you can see that there's perhaps some overlap on what people call filaments or what people call nodes. You see there's a variety of scales at which things are considered. There's a variety of different assumptions in each of these methods. And if you look at the density, the overdensity of halos in different environments, you can see they actually vary wildly from one method in another. So here, what I have in the x-axis, I've got a measure of overdensity, and the y-axis just have a probability distribution. And if I just get you to look at the bottom right that says voids, you can see that everybody agreed that voids are underdense. Okay, easy. But when you go to nodes, you can see actually there's a variety of densities that people associate with something they've identified as a knot. And so it's really difficult to say what's right, what's wrong. There's no truth table. You might want to think about, okay, maybe I can parameterize maybe the cosmic web in a way that allows me to encapsulate most of the information on it. So Paco's been doing that. There is easy route. Paco's been doing that a lot. But there's no real way of defining it. So for the purposes of today, we're not going to go into this anymore. But you'll notice as I go through lots of different slides that there might be slight different measurements of the cosmic web environment. And as much as I was in control, I tried to sort of establish the effect of that. Sometimes I wasn't in control, but it's just something that today we're not going to go into a lot of detail about. So now I want to link the cosmic web to this idea of assembly bias and the Galaxy-Halo connection. So what I have here is on the left-hand side, I've got two plots, so just focus on the top one. What I've got here is effectively a correlation function, and you see two samples, the closed and the open squares, and they are the correlation function of halos at the same mass, but different. They are in different environments as defined by the tidal tensor, so different cosmic web environments. And you can see there's a difference. Here, much later, here's another plot, which is slightly easier to interpret, and you just got halo mass on the x-axis. You've got linear bias on the y-axis, so how much they cluster. And again, the different colored lines tell you about its cosmic web environment. And so there's this sort of coherence in the literature that says, okay, there is clearly a dependence of the clustering of halos according to their cosmic web environment. Now, why is that? And so I'm going to just take you through very quickly through a really beautiful paper. The references under this, so you can see it. These are the ZOMG simulations. So zooming on a mobile galaxies is not my work at all, but I found it really, really interesting and really helpful in clarifying my view of what's happening to these halos. So what you've got there is two halos. They're simulated halos. This is a zoom-in cosmohydro simulation. They have the same mass at redshift 0. The one on the right, okay, is stalled, so it's no longer accreting, which means that it's old. It stopped accreting a long time ago. The one on the left is still accreting, and it's young. And you can see just by looking at them that they look quite different. Okay, so the substructure is different, for example, and if you could plot other properties, you would see some differences there. So what I'm going to do now is zoom out and look at their logical environment. And so the halo on the right is embedded in a filament, and the halo on the right is one where most people, most classifiers would say it's a void, but you can see these sort of tiny little, sort of sometimes called tendrils of material coming in. Now the color tells you the sign of the velocity of the material in the rest frame of the halo. So red stuff is going away from the halo, blue stuff is going into the halo. And you can see that the one here is that it's in this filament. So it's accreting at a much lower rate, but also it's accreting only in the direction that is perpendicular to the filament, because within the filament, material is going towards the nodes. So logical structure will tell you that material will go from underdense regions to overdense regions. So they'll go from voids, sheets, then they'll travel to filaments. Once in the filament, they'll travel to a node. And so this poor halo here cannot do very much, so it's not accreting. This one here is happily accreting, happily growing, and is doing so in a much more isotropical way. And so you can, I mean, this paper is really nice. It will give you sort of lots of different sort of a really good picture of what the cosmic web might be doing to halos. So just to summarize, so you've got a difference in the anisotropy of the orbits. You've got a different concentration, you've got a difference in substructure, and you've got a difference in where they form in the initial density field. And so this allows you then to link this cosmic web, this assembly bias, right? So this predominantly works at lower mass. You've got these halos, okay, that are within filaments. They cannot accrete, and they are in regions of strong tidal interactions, but they are in regions typically near nodes, and therefore they have a higher clustering. And so these stalled halos that are old, okay, they cluster more strongly, they are older than halos that have the same mass at redshift 0, but they are free from these sort of constraints, tidal constraints from their environment. And so in 2019, at least, there seemed to have been an agreement that the cosmic web seemed to be key in looking at assembly bias in terms of halo assembly bias. But what about galaxies, the galaxy properties and the galaxy physics? I mean, does that matter? How should we think about that? So can we link these two? Can we link this picture that I just showed you of these halos growing or not growing in the cosmic web with the galaxies that are in them? So one way to do this, so this is now reasonably old work from 2017, but what you can look at is a proxy for halo age. So remember, if you remember that stellar to halo mass relationship, a fixed halo mass, higher stellar mass means the halos are older. So you can look at a stellar to halo mass, a fixed halo mass as a proxy of halo age. So this is now in observation, this is now in gamma, where you have in the x-axis is different environments according to the cosmic web. On the y-axis, you've got stellar to halo mass ratio, which I'm going to take as a proxy of halo age. And then the different colored lines are different masses, halos of different mass. And so you can see, if you just don't look at the shape of the lines, if you just look at their rough amplitude, then you see that the lower mass one is the purple one, and then it goes to red, green, and blue. So it goes up and down, and that's the shape of that stellar to halo mass relationship that I showed you before. So that's it going up and down. But then at fixed halo mass, so within a color, you see that there's a difference between voids and knots. So this ratio increases as you go to knots, and these are the older ones, right? So this was indirect evidence that the cosmic web is affecting halo growth by looking at the stellar to halo mass relationship. What about the properties of the stars within those halos? That was really hard to tell. So if you've ever played around with gamma data, you'll know that Spectroscopically, there's not a lot to, it's really hard, there's low signal to noise. And I was predominantly looking with spectra. So there was low trend, there was no significant trends at all with things like age, metallicity of the stars. However, we did full mocks and with the gamma signal to noise ratio. And so even in a simulation where we knew assembly bias was there, in our mocks, we didn't recover it because of the quality of the data. So we didn't find anything, and that's perfectly consistent with the quality of the data. Okay. Now I want us to think about, okay, so let's say, we're going to work this point a bit more later, but let's say that the cosmic web does impact on the property of galaxies. I want us to think a little bit about how. Because you have two ways of doing this. Because one way is just, okay, maybe the cosmic web is just affecting the dark matter halos. It's modulating their growth. And then the growth of dark matter halos propagates onto the galaxies, because we know they're linked. That could be one way. So once you've established the properties of dark matter halos, their assembly histories, you don't need cosmic web environments anymore, because they've done their job by modulating the dark matter halo growth. But there's another way to think about this, in that the cosmic web affects the properties of galaxies, or affects this connection, the galaxy-halo connection, in itself. So beyond that modulation of the halo assembly history. And so here, the sort of orangey, reddy arrow is the galaxy-halo connection, and we're trying to understand how the cosmic web affects it. And if you think about sort of how the relationship between, halos on the left and galaxies on the right, that relationship is really, really complex. And so there's a number of things, a number of baryonic effects that could be happening that actually could turn this top one, this link between cosmic web, dark matter halos, and galaxies, to turn it on its side. And I don't have time to go into it, but Wei-Wan Kui has got some really nice stuff on Simba. Okay, so I want to give you a world tour of what people have found in terms of how the cosmic web affects the growth of galaxies. So we're going to look at things like total luminosity, stellar mass, star formation rates, and we're going to look, because galaxies grow with halos and the cosmic web modulates halo growth, so we ought to find something. So here's an example where we've not found anything. Not me. So this is work by Lizzie Early and Gamma, now back in 2015, where what you're seeing there is a luminosity function split as a function of cosmic web environment, okay? And to first glance, it looks like there's a clear separation between sort of cosmic web environment and the luminosity function of galaxies. But actually, what she then done is she's tried to say, okay, is this just down to density? Because we know that just over, your box standard friendly sort of spherically averaged over density correlates with cosmic web environment, and that knots are predominantly in overdense regions, voids predominantly in underdense regions. This is obviously not a one-to-one relationship, otherwise we wouldn't be discussing the cosmic web, but they are correlated. And so what she's done is said, okay, I'm going to take the galaxies in each environment, and I'm going to shuffle, I'm going to redraw my galaxies such that I have the same overdensity distribution as my original sample, but now I'm going to throw away the cosmic web environments, I'm going to mix them in, and she got exactly the same thing, which means that it was overdensity that was driving her result, and not the cosmic web. Another sort of work of Katrina Kalic, who's done some really amazing, beautiful, clear work on the impact of the cosmic web on galaxies, actually shows, so you don't see it here, but the x-axis is distance to filament. Yes. And what you're seeing here is that the distribution of galaxies is different depending on where they sit with respect to a cosmic web. So here, this is a different estimator, is just telling you how close are you to a filament. And in this case, she used the same shuffling technique, and actually she found out that it was the cosmic web and not overdensity that was driving this relation. So galaxies closer to filaments seem to be more massive, at least in this work. Now, there's a variety of works, we're not going to go through them together, But if you bring them all in, then the picture that seems to be assembling is that galaxies near filaments have redder colors, they reduce star formation rate, so they're not growing, therefore they are quenched. And so this is just a variety of works that show that. That ties in really neatly with our picture of halo growth. So there's also a really neat result in this. So I just want you to remember this plot in stellar mass, the halo mass, and here this is color coded by the halo, by the age of the halo. And so this is work that you might be familiar with because it came from here. This is Laura's work that's showing now, looking at the age of the stars in galaxies in SDSS, a similar trend that again seems to suggest that the age of the stars is going with the age of the halo. Now the picture here is way more complicated. So this whole, even the plot on the left is sort of a hotbed of discussion in the community, because if you look at lensing, you actually find that it's the blue galaxies that tend to sit on the opposite side of this. And we can talk about this at length offline if you want to. Okay, so, but I really like us to think about, okay, in which of these boxes are we? And nothing that I've showed you sort of allows us to distinguish between the two so far. So I want to highlight work by a PhD of mine, Harry Chittenden, who, for other reasons, designed a recurrent neural network that from the halo assembly histories would predict, well, and a number of other things, would predict a star formation history and a chemical enrichment history, okay? So he asked the question, can I predict the assembly and the formation history of galaxies from only dark matter properties using machine learning? And if you do that, then once you have a star formation history, which tells you the age of the star as a function of time, you can integrate that. This is done a posteriori. You integrate that to get a stellar mass. And actually, you get really beautiful agreement with the original stellar to halo mass relationship. But also, what you get is that he actually, the neural network does predict, if you just look at the top color plots here, the original one has that gradient that I've showed you so many times already today, and the predicted star formation histories have the same thing, okay? And what's interesting here is that the cosmic web, throwing in cosmic web information does nothing to this. The plot keeps the same, which really means that the cosmic web did its job by modulating the halo assembly histories. Once that was done, there was no more information needed from the cosmic web in order to predict this relationship. And so this sort of made me think that in this case, when we're looking at sort of the stellar mass and the stellar ages, we're probably in that case over there. But you can think more broadly. There's more to galaxies than stars. So one of the things that people have been very interested in terms of the cosmic web is obviously gas content. And so many people have looked at sort of the content of neutral gas in relationship to the cosmic web. And why should we look? Well, we know that neutral gas accretes onto galaxies and therefore turns into stars, but it also can impact on things like metallicity. And here the picture is actually less clear. So this is a clear example. This is again on the x-axis, you've got distance to filament, you've got H1 deficiency on the y-axis. And what it's showing you is that as you go closer to a filament, you have a deficit of H1 gas. Okay, and this was done at, controlling for things like stellar mass and controlling for things like the least surface density. But there's other works, and the picture is less clear. So these things really seem to depend whether you associate excess or deficit of neutral gas in a galaxy with respect to its position in the cosmic web. Depends highly on what you mean by cosmic web, depends highly on the mass that you're looking at, and depends highly on how you measure your H1 mass. So here the picture is actually much less clear, and I think this is one of the sort of really interesting things that is opening up now, is this will become a lot clearer in the next sort of 5 to 10 years. I'm not going to talk about that. I don't do neutral gas. I don't do gas at all, unless it's ionized, because then I can see it. Because then I can see it in the emission line. So I do optical stuff. And so what we did, we looked at the metallicity of the ionized gas in galaxies. Okay, and so why do we want to look? Well, the gas metallicity increases of star formation. So generations of star formation increase the metals in a galaxy. But also the gas metallicity decreases as it accretes pristine neutral or pristine metal poor gas from the cosmic web. So you've got these two competing things, and we want to know, can we disentangle them? So this is work that was done by Callum Donnan. So Callum Donnan was a master's student of mine at the time. He's now gone to find high redshift galaxies in WST, so he doesn't think about this anymore, but I'm hoping to get him to think about this again at some point. But anyway, before he went on to do all those wonderful things, he was doing this with me. And so what he found is that there seems to be a small but significant difference in the metallicity of gas, metallicity of ionized gas in galaxies according to where they are in the cosmic web. And this is perhaps better here in these plots. So what you're looking at, just look at the bottom two plots that have just popped up. So on the x-axis, you've got distance to filament or distance to node. And on the y-axis, you've got the residual to the median relationship, to the median metallicity mass relationship at that mass, fixed mass. And so what you see is that, especially for nodes, you see this decreasing trend with distance to filament, such that if you're closer, distance to node, if you're closer to a node, you are more metal rich. If you're further away from a node, you're more metal poor. It's also there in filaments, but much more tenuous. So this was all done in SDSS Galaxies. Sorry, this is your box standard SDSS catalog. Okay, so then we looked, okay, can we infer why this is happening by looking at TNG? So now this is the same. So let's just TNG is the Cosmo-Hydra simulation. In principle, you have everything you need to disentangle this. So now you're looking at effectively the same plot again, and you see the same relationship. It's slightly amplified. The direction is the same. It's amplified with respect to nodes. We track that down to the comparable number density between the two samples. So so that we think we understand that difference. But qualitatively, these galaxies in the simulation show the same trend between metallicity and distance to the cosmic web. So then, so this is the same plot as before, but now in the simulation. I forgot to say before, so I've asked you to look at the sort of the solid lines. There's some dashed lines, some dashed blue and red lines, and those are what you do when you shuffle away the distance to filaments, but you keep the overdensity information, and the signal goes away, meaning what's driving this, it's not spherical overdensity, but it does seem to be the cosmic web. So then you can ask, okay, why is this happening? Okay, so what you've got here is the star formation histories of the galaxies in two samples. So just try to make things clear, we just picked the 10th percentile further and the 10th percentile closer to nodes. And if you just look at the top curves, okay, what you're looking at is the star formation history. And you can see what you'd expect from that halo growth picture that marginally, the ones that are closer to nodes, the galaxies that are closer to nodes, form their stars earlier, slightly earlier, not by a lot. But this is consistent, for example, with Laura found. So not a lot, but it's there. But that actually, you can see then the impact of that on the chemical enrichment of the stars. So in the bottom, you have the stellar metallicity, okay, the stellar metallicity history of those galaxies, and you can see that that sort of earlier formation then led to an enrichment of further populations and sort of sped up the metal enrichment of those galaxies. You can also look at the gas fraction simulations, okay, and so what you see there is at fixed stellar mass, you're looking at the gas mass fraction in things that are close or far from nodes, and you can see that in filaments there's really very little difference actually. But it notes that there does seem to be a difference, and sort of it goes in the way that you'd expect, in that galaxies closer to nodes, they have a lower gas mass fraction, therefore potentially not having access to this metal poor gas, and therefore they have a higher metallicity. Now, I don't have final results to show you, but we have sort of ongoing evidence to believe that actually the mass assembly history of the galaxy is not sufficient to explain this. Okay, so there definitely seems to be something else going on that a fixed assembly history of a halo, so halos that assemble similarly, depending on where they sit in the cosmic web, you do seem to see a difference in their gas content, in the gas metallicity, which wasn't the case in the stellar ages. So there's some nice work, some recent nice work that I want to highlight. This is by Annalise Antonio's group at UCL, where they've got this new method of estimating gas masses. This is OSDSS data again. And what you see on the left is the metallicity mass relation again, and then it's split in sort of regions according to its scatter. And then if you look at and then what you've got there is estimates of the gas mass. And so what you have is that a fixed stellar mass, okay, the ones that have a higher metallicity, so the purple curves, the ones that sit above the median relationship, they have a lower gas mass. You can see that in the middle panel. They associate that with lower accretion rate. These are your stalled halos. These are the ones that we said are going to be closer to nodes, and there will be higher metallicity, which is what we see in the simulations and in here. So again, it does seem to be that this is all consistent with the cosmic web having an impact on metallicity, and more so one that I can't really just explain with the mass assembly history. That's good. So I just want very briefly, in the next sort of 5 minutes, tell you about something else that we thought about. And this is motivated by this plot on the left. So if you go back right to the beginning of this talk, I showed you this plot to motivate assembly bias. And I sort of said, there seems to be a difference in how halos cluster according to their the orbits of the particles in the halo. And then I showed you those beautiful zoom-in simulations that sort of gave us an intuitive picture of what was going on. I had a student who was working on this, and he was finding differences in the anisotropy of the orbits according to where galaxies were within the cosmic web. And also at the same time, there was this sort of initial work that, okay, so you can see the thing at the bottom here. This is work by Genital, and what you have here is looking at the misalignment of stars and galaxies, so how they are moving, stars and gas, and how they're moving in a galaxy. And what you have here on the y-axis is neighbor count, and this was then turned into a sort of environment measurement. And we noticed that misaligned galaxies seem to be predominantly in these underdense regions. Well, could these be these young accreting halos? And could you still be seeing signs of that accretion in the disturbance of the kinematics of the galaxies, as shown by their stars and gas kinematics? So Chris, he was a brilliant PhD student, thought about this long and hard. He looked both at data, so he looked at manga, and he looked at simulations where we did sort of simple but effective mocks of manga mocks of galaxies. And so you can see some examples of a misaligned galaxy. So the top galaxy is aligned in that the velocity fields of the stars and the gas are similar, but the velocity fields of stars and gas are different in the second example. And so could this be a signature of halo assembly? And so we looked at a number of things. I'm not going to take you through them in detail. We looked at the stellar to halo mass, because we know that's correlated with halo age. We looked at halo occupation distribution. So this is just telling me how many satellites there are in a given halo. And this is because it's related to substructure, and we know that's linked to halo assembly. And then we also looked at location in the cosmic web. We found absolutely nothing. Okay, so there was really no correlation whatsoever between star gas misalignment and large-scale tidal field or anything to do with the cosmic web at all. They were completely ignorant. So the inner regions of the galaxy, this is up to 2.5 effective radii. Most of the galaxies are about 2.5 effective radii, completely ignorant of the galaxy's large-scale environment. So instead, what results showed was a scenario where gas accretion from the hot halo actually stochastically misaligns the galaxies. So we found this, right? Nothing there. Chris decided to think about this a little bit further, and they started to look at linking the misalignment with halo formation history via angular momentum. So he noticed that all the misaligned galaxies had a lower angular momentum. And then, so the top plot is on manga, the lower plot is on illustrious TNG, where again, it's tracing down. So these are, sorry, you don't see the x-axis, so that's just redshift 0 over here, higher redshift there, they go up to redshift of 1, these plots. And the different lines are different types of galaxies, misaligned or aligned. And you can see that at redshift 0, by definition, by construction, they separate, but they actually separate all the way up to redshift of 1. And so what he found is that galaxies that are currently misaligned have a lower angular momentum in data and simulations. And then simulations, you can actually trace that back to redshift of 1. And so what he proposed is that, okay, star galaxy misalignment redshift 0 is correlated with angular momentum of the halo down to redshift of 1. And this is correlated with halo simple history. So then what you have is that if you're in a halo, if you happen to be in a halo that has a lower angular momentum, then you have a lower stellar angular momentum. We know these two are correlated. There's lower torques, which means that if you happen to become misaligned, then you continue to be misaligned for longer. And therefore, you're more likely to be seen, to be observed, being misaligned. So then this came back to this. So we don't really know where we sit here. Unfortunately, Chris is putting his brain power helping the NHS, the National Health Service in the UK, which needs his brain a lot more than astronomy. So this work is currently paused. Okay, so just to go back to where we were, sorry. I tried to get us to think about, you know, where do we sit in these two ways? I can't really tell you. I can tell you that this is complicated. I can tell you the cosmic web is sort of this multi-scale, multifaceted thing that affects not just the growth of halos, but it also affects the growth of galaxies. I told you about centrals. I didn't tell you about satellites, and I didn't tell you about groups because I didn't have time. We're well out of time. I think in most cases, okay, when you're looking at very simple things like total stellar mass and perhaps the age of the stars in a galaxy, I think a simple model that goes via halo growth is sufficient. So that's what you're interested in. That's what you need to make mocks or whatever, then I think that's fine. But for other things, for understanding galaxies and a little bit more complexity, then that will not be sufficient. And that's it. I will leave you my summary. I think for another time. Thank you.
Thank you so much, Rita. Questions from...
Hi, thanks a lot for your very nice talk, very interesting. So I was wondering if the final correlation that you find between the misalignment redshift 0 and the general, let's say, angular momentum of the dark matter halo up to redshift 1, is that relation broken if your galaxy go through mergers of different types? How do we?
Yes, so these were mostly isolated galaxies, you're right. So I think if we look, and we did the same thing in the observational work that we did, I didn't mention it, but we tried to at least look at galaxies that didn't have a clear disturbance of redshift 0. Yes, this will get muddled with mergers.
And if I can, another quick question. You see no signal with the inner part of the galaxy for the other relation you were looking at, but did you look at something, at least in simulation, did you look, because in observation is difficult, but in simulation, do you look beyond 2 effective radius?
Yes, so this is what motivated this plot here. So what this is showing is actually then the velocities of the satellites. So then we went to the other scale. So we look at the velocity of the satellites in the halo, and that definitely shows something in simulation. And in observations, we're thinking perhaps what we can do is stack these. Okay, so we could stack groups, okay, and align them with respect to nearby filaments, then perhaps you can then see something. But I mean,
But in simulation, you found.
in simulations, we find something directly, but finding an observational probe for that is difficult.
More questions? Oh.
Hi, thank you very much for your nice talk. I have some very basic questions. So what is the definition you would stick to regarding assembly bias?
So, well, the way I've motivated this at the start was just any secondary halo property that impacted its celestial amplitude that wasn't halo mass. In the context of the cosmic web, that becomes very much linked to the halo age and the halo kinematics. So those are the two things that I explored directly in these things.
Because if there is already a dependence on the local density, then that would be, according to that definition, already assembly bias. And I got a little bit confused with some study you showed where they shuffled the density locations and they found no.
That one.
Yeah, yes, exactly.
Yeah, that's right. So they found, so this is what they found. They found here that any dependence on the cosmic web could be traced to the dependence on overdensity completely. So, but that is not always the case.
Okay, I understand, but still that would be assembly, a kind of demonstration of assembly bias, even if it's only dependent on the local density, because what we get from outside, not being inside this whole discussion, is that there's not a complete consensus about assembly bias and whether it's significant or not. And well, from the studies you've shown, I think you show a lot of evidence. And it seems robust to me. And my final question would be, what is the consensus in that field about assembly bias and whether it's accepted for the galaxies and to what significance level?
So for the galaxies, I don't think there is a consensus, right? I think for the halos, there is. I don't think there is for the galaxies. And I think that it depends a lot on what you're interested in and what your goal is, whether you're trying to make mocks or whether you're trying to understand galaxies. But no, I don't think there is a consensus.
Thank you very much.
More questions?
So you need to understand why and how it impacts. For example, I wonder what the relationship between the galaxy and the planet and the 2000
Is there a way of putting the question?
Yeah,
Can I? Okay. Oh, I've got chat. Hang on. I've got it. Does the simulation also have the same galaxy cosmos life? Yes. If so, it should be easy to understand why and how this happens, right? No. Furthermore, I wonder whether the no relation between galaxy cosmos life and cosmic web is okay. Good. So these are all excellent questions. So there are three questions here. First one, does the simulation also have the same galaxy cosmos alignment as the observations? And the answer to that is sort of yes. So this is a comparison between TNG and manga separated according to, so this is just a histogram, if you will, of the different levels of misalignment according to the type of galaxies in manga and TNG. They're not quite the same because we couldn't quite get proper morphological distinctions in TNG, but a proxy for that. So the answer to the first question is yes. If so, it should be easy to understand why and how this happens. So this is what I always think when I go into simulations, and the answer must be in there, right? And actually, it's really, really difficult to assign causality to things because often what you're looking for, are where you find are correlations, and then trying to induce causality, I think it requires you to come up with a physical process that might be causing that correlation and then test that directly. And that's what Chris tried to do first with the angular momentum link, and then in the second paper with black hole activity. Okay, so yes, it is possible. I don't think it is easy. Furthermore, I wonder whether the no relation between galaxy gas misalignment and the cosmic wave is caused by the cosmic wave finder or simulation resolution. This is absolutely possible, and this was also at the time we only have half of the manga galaxies. Would really like to revisit this with more robust cosmic wave estimators. Also, DESI is coming, so we're going to have really nice cosmic wave environment for manga galaxies. So this is definitely something worth revisiting, but with the level that we had, we didn't find anything. I hope that answers your questions.
More questions in the room? Or people over Zoom?
Okay.